As you may know, I'm the one that was organizing the speaking program for this conference. And I think I did a really lousy job because I scheduled myself in this panel to be the very last thing. So I do have a little compensation for you as Quera socks, if you can pass them around. I'm already wearing mine. So, so thank you very much for staying so late. And those of you that have been following my podcast, the Superposition Guy, know the first question, and maybe we start with Mercedes. So who are you and what do you do?
Um, Hi, everybody. So my name is Mercedes Gimeno Segovia. I am VP of System Architecture at PsyQuantum. I hope you all had a chance to hear the talks from two of my colleagues. Pete Chadwell, our Chief Scientific Officer, gave a keynote explaining a little bit about what we have been doing and the progress we've made in the past year, as well as only just recently our Head of Applications, Sam Pallister, talked about some of our work in our area. PsyQuantum is really a kind of a full stack company. We have teams that work on fabrication of devices for photonic quantum computing. We have teams that work on architectures, both from the kind of the lowest level all the way up to implementing error correction, logical applications, logical operations and applications, as well as the software that we use to both design and run such applications on our systems.
Wonderful, Dave. And you?
Yeah, so I'm Dave Landheis, and I manage the quantum fleet engineering team for Google. What that means is the people on my team are responsible for building Google's quantum computing systems and for operating them as platforms that researchers can use. And we also engineer how we build and operate the quantum computers with lots of specialized tools and software. And I think, as many people know, our hardware development effort at Google focuses on superconducting qubits on chips, and we now have a very substantial effort towards error correction. We even recently modified our mission statement, so now it says that we will build large-scale error-corrected quantum computers that whose benefits are universally accessible and useful.
Wonderful. Theo?
Hi everyone, I'm Theo Perronin. I'm the CEO and co-founder of Alice & Bob. At Alice & Bob, we're building a universal fault-tolerant quantum computer, also using superconducting circuits, but a new breed of qubits that are called CAT qubits, just like AWS, and they announced a logical qubit. We're still to see the paper, but very looking forward to it last week. And so the claim of CAT qubit is really to be hardware efficient, meaning having a first level of built-in error correction to dramatically simplify the design of the overall machine, slashing the overhead requirement by, we claim, 60-fold. So it's sort of a fast track to fault tolerance.
Earlier in the conference, I was introduced, or Quera was introduced as the company that makes the lanyards that you're wearing. This is the third day. You know, we also make shirts and socks. And then we also make neutral atom quantum computers, and we were sort of part of the Harvard Quera MIT announcement of the logical qubits, but I'm here just to moderate. So my first question to you is, why is your approach the better approach for error correction? Or why is your modality the better approach for error correction? Who wants to go first? All right.
All right, I'll go first. So PsyQuantum was focused from the beginning, and the beginning is now 7 or 8 years ago, on fault-tolerant quantum computers. And we were really convinced that in order to achieve fault tolerance, we would need a large number of qubits, meaning a large system. And so when we started looking at our approach, we were really focused on what enables the scaling to that large size. And if we look at what are the biggest systems that exist today for computing, and in particular, how do we leverage their size, there is all thanks to optical interconnects. So photons are already like the perfect qubit to interconnect quantum processors, and you can make architectures that are kind of very scalable, very manufacturable, already for those qubits that are that are going to enable you to go to those large sizes. So really for us was, I mean, obviously we were like our background was in photonics, but really the focus was what is going to enable that large scale, that large scalability and the manufacturability that needs to come along with it in order to build those large systems. And so that's where we focused on. And all of our work in terms of codes, in terms of the development of devices has been focused towards those large systems.
And Russell, thank you. I know you're a really busy speaker and you were rushing across the hall. So 2 questions for you. One is, who are you and what do you do? And the second is, why would your approach for error correction be the best approach?
Okay, let's see. How do I turn this on? Okay, is this one? No. Oh, okay. First, apologies. Yeah, I was coming from my other talk. Tough scheduling here. So I'm director of commercial hardware at Quantinuum. I kind of lead the teams that are building and designing our quantum computers that we launch commercially. And why is our approach the best approach, right? Well, I think there's a lot of things to explore in quantum error correction, and no one really knows all the final codes that will be used, the final modalities. But we do have a very versatile quantum error correction code testbed because we have a combination of qubit traits that I think make it a very versatile QEC testbed. We have very long coherence times, which gives us the ability to do readout and decision making in real time and do real syndrome extraction cycles in real time and even algorithmic decoding in real time, and high gate operations, and then all-to-all connectivity, which allows you to explore codes that are not just nearest neighbor, but need higher connectivity, live on kind of higher dimensions. So I think for those reasons, I think it's a very promising avenue to go pursue quantum error correction and help get us to the fault-tolerant era.
And Theo, and then Dave.
Yeah, so at Alice and Bob, the approach is, the philosophy is really about hardware efficiency. And so what does that mean is that we build slightly more complex qubits that occupy the same footprint, but that are a bit heavier in terms of maths behind it. So those qubits, what they do is that they embed a first level of error correction. Natively, they suppress exponentially bit flips at a linear cost on phase flips. They are the so-called bias noise qubit. And what that allows us to do is to correct only for the remaining phase flips through redundancy. So there we claim a square root factor improvement in terms of overhead. So when you look at the numbers, we publish the architecture, and so what we claim, for example, is that on the benchmark of running Shor algorithm to break RSA 2048, we go from 20 million with the usual approach to down to 350,000 qubits. And when you think about it, the cost of a single qubit is nothing. What actually costs in qubits is the control electronics, all the environment, the enabling technology that are required. And this scales linearly with the number of qubits. So when you reduce the requirement interval number of qubits, what you actually reduce is the cost of the machine directly. So I guess this is the main advantage in our case.
So we won't claim that we can be sure that we are using the right approach, but we feel like we at Google have made a lot of good progress using a 2-dimensional grid topology of superconducting qubits, which I won't say is easy to make, but we know how to make them. And we have demonstrated very good fidelities for single and 2 qubit gates. And so we think that's a good baseline to start with. And with our demonstration from the last year that we can do a logical qubit prototype, we think that it's still very promising to continue working along this path.
And we got lucky here because we have 5 different modalities on stage, which is really cool. Today, before error correction, there are error suppression algorithms, there are error mitigation vendors. Do you think they're just going to disappear when there is error correction, or is there still room for error suppression, error mitigation once logical qubits appear?
Maybe I'll go first. So I think that, those techniques are just net gains. But when my vision of it is that those are sort of linear solution to an exponential problem. whereas quantum error correction is really an exponential solution to an exponential problem. So they're just not playing on the same league here.
A lot of it depends on what we're defining, right? I think in some ways the cat qubits are a source of error mitigation, right? And it makes the error correction easier. So I think there's other potential ways of using these mitigation techniques that could be in the long-term future where you combine them with QEC to make the QEC easier to produce and cheaper, right? So if we count those, I think that there is a long-term future. I think some of them could be used earlier before we have a fully fault-tolerant machine. And I also think even if we have fully fault-tolerant machines, it's not completely obvious to me that we wouldn't still have smaller machines to possibly perform other things, including education and so forth. So it's not clear that the most powerful machine is the only machine you would ever build and operate, right?
Anyone else want to?
A brief answer. As the previous panel pointed out, error suppression is pretty much always a good thing. So why wouldn't you do it? And to just follow on what Theo said right here, error mitigation is not a solution to an exponential problem. So we like to talk about the exponential wall that you hit when you have errors in your gates, because the error appears in the exponent of basically the error that occurs with each gate. So you need something more than error mitigation when you talk about practical quantum algorithms, which are going to have billions of gates in them.
We spoke earlier about the advantages of each approach, but let's go to the other side. What is the most difficult issue with the modality that you're using? Mercedes?
All right. I assume to get all the hard questions first. Sure. So photons are a very different type of qubit than other qubits that are manufactured devices, because photons are particles that are created and measured, and when they're measured, they're destroyed. And not only that, but as they go through the different operations that we do on them, there's always a chance of having loss. Actually, this is something that then leads us to think much earlier on ways of mitigating the qubit exiting the computational space erasure. In John Preskill's talk, he talked about dual rail qubits and encodings for other types of qubits. That's something that has been kind of standard since, I don't know, the 90s or something, for photonic qubits, because it's a challenge. So not only are we looking at reducing the type of noise like Pauli noise, but also erasure. Now like loss or erasure. The good news is that all the codes that are good for Pauli's are about 10 times better to suppress loss. So it's not all a loss gain, but yeah, let's say keeping our photons alive is one of the main tasks that we're paying a lot of attention to. And this will also be applicable to whenever any other technology are trying to use photonic links through transduction, for example, in order to communicate various QPU, like quantum processors. This is another challenge that they will have to look at as well.
So Theo, keeping the photons alive is a problem. Is keeping the cats alive a problem, or is there something else?
No cats were harmed in the process. Yeah, so in my case, I guess what keeps me up at night from a technical point of view is kind of a drawback of an advantage of solid state qubits, which is they're fast. And so what that means is that you also have to be very fast at decoding errors. So with our vanilla architecture, it's just a repetition code. The decoding burden in terms of classical compute is extremely slim. With the novel architecture we'll be releasing in January, further reducing the overhead, we'll move back to the same kind of decoders as surface code. And so then the challenge is to find classical electronics that are very cheap because you're going to need a ton of them and fast enough to follow the qubits.
Dave?
So I would say scaling is one of the big challenges that we face in superconducting qubits, and every qubit tends to need multiple control lines. It needs a way to be read out, and we operate, of course, at near absolute zero. And when you start to scale up, it means you need very large cryostats as well. And right now, all these things are expensive. And so if you think about per qubit cost, that is definitely a challenge for the superconducting qubit community.
Russell?
Yeah, so I think a lot of people like to say, trapped ions can't scale. I tend to disagree strongly. I think they can scale, and we are scaling. I think there's certainly technical challenges like any modality, but that all looks quite feasible to me, to be honest. But I think the biggest challenge in the scaling is what John Preskill mentioned this morning, which is the wall clock time, right? So I think our ratio of kind of operation speed to coherence time is quite good because the coherence times are so long, but at some point, wall clock time matters as well. And so we do have to speed up operations. I think we have some paths to do that. I think the first one was to demonstrate really low heating junction transport at good speeds, which we did recently, and that's going to be very enabling over the next coming years. But then we need more orders of magnitude. I think there's probably 1 or 2 orders of magnitude in just transport speeds. I think you can also get some big wins potentially kind of doing time-space trade-offs, either algorithmically or at the physical layer. And so I think there's paths forward, but I think that's the most challenging part.
Should I answer my own question, or would you like me to move to the next one?
No, please do. I think it will fulfill the panel.
No worries. I think for neutral atoms, the concern that people have is speed, meaning how many shots can you do a second. Now, the gate speed itself is super fast, but the things that really take time is one is the loading of the atoms. And in today's computer, it's like a Connect 4 game. When you finish the calculation, so you pull the lever and all the pieces fall out and you have to start again. And then on the other side, the measurement uses a camera, and cameras have, they need enough photons and they take a little bit of time to read out. So the solutions could be, and I think Vladan Vuletic spoke about it this morning. One is sort of what we call continuous reloading, which is to say, not just throw all the atoms and load a whole bunch of 10,000 new ones, but as you use them for mid-circuit measurements, sort of have a little factory that keeps loading atoms into the chamber. And then of course on the cameras, we can work with camera manufacturers, we can consider non-camera sensors and so on. But I don't think we'll ever get to sort of superconducting speeds in terms of clock rate, but I think there's really a lot of room for improvement. Many of us work closely with universities or researchers and so on, and my question is, what do you see typically as the lag time between, oh, we published a paper that shows XYZ and that system actually being available for people to use? Well, maybe Dave, we start with you on this one.
It's a good question, and it particularly at Google, we are taking a little bit of a different approach than some of the other companies, in that we're choosing deliberately to work with a small circle of experts instead of trying to provide a generally accessible service at this point. We feel like that maybe is the most efficient way to make research and development progress towards the fault-tolerant computer. But that being said, our goal is to, within this circle of experts that we're working with, is to provide them with the state of the art very soon after we have demonstrated it for ourselves.
Theo, perhaps, and then Mercedes.
Yeah, so in our case, we go sort of for a hybrid approach, meaning that we have 2 levels of engagement with the academic world. The first one being with our closed circle. We're spin-off from several labs, and we remain in symbiosis with all those labs, sharing PhD students, having weekly meetings. I believe most of our publications are co-authored by academic labs. And then here we're really in the same spirit as Google. But then we're also working to put our devices on the cloud so that, I mean, the broader audience can start playing with it. And something I really appreciated in what Google did in their surface code demonstration was to provide the data set to the academic world and let so many researchers play with that, try out different decoders. And I think it's really beneficial to engage in this tight feedback loop with the academic world. So this is why we want to broaden our audience that way as well.
So the modality in which we engage with the academic community is twofold, depending on what side of the stack we're talking about. So if we're talking about architecture stack, software, applications, there's a lot more engagement with external parties, either customers in some cases that are interested in some problems that we're co-developing, or academic groups that are interested in certain areas. On the hardware, it's a little bit different because a lot of the development is really proprietary and is done kind of internally in-house. So, and since at the moment we're not offering access to our internal hardware milestones, then those engagements are significantly different than what we do at the kind of architecture and applications level, which is a lot more kind of open and we discuss with the academic groups.
And Russell?
Yeah, so I mean, it really depends on the innovation, right? So there's things like we partner with academics to do demonstrations on the hardware. Those demonstrations are typically done on the commercial hardware itself and kind of immediately available to our users. So things like demonstrating non-abelians for the first time or something, our users could go recreate that. But then if you're talking about, okay, now partnering with them to do some, a different qubit or something, that's a much longer time scale to incorporate into the hardware, of course. But if it's a new protocol for performing some operation, it just depends. It could go kind of immediately to a very long time lag, right?
I want to take some questions from the audience, and I have some more questions later. But while the audience thinks of their first questions, I have a question that I like to ask everyone that's a guest on my podcast, which is a hypothetical. So if you could have dinner with one of the quantum greats, dead or alive, who would that be? Who wants to go first?
You got to say Feynman, right? Like, I didn't want to go first and steal him, but no one else stepped up. So that would be very interesting to, I think it was great in the QEra talk where Vladimir was talking about, the vision he had of using individual atoms. And now to actually, it still gives me chills to see us be able to control these things down at the atomic level and have such precise control. And I think it would be thrilling for him to see that vision where we're actually operating on individual neutral atoms or atomic qubits, or even the kind of man-made, human-made qubits. I think it would be a really interesting conversation. I think you might be quite impressed at where we're at.
And Mercedes, who is your dinner guest?
I think, well, since you stole Feynman,
sorry,
I'll say Bell, because I think it would, if we think about, what the Bell inequalities gave us all that time back, like it was kind of the first inkling that something might be different, and that something, I don't think at that time it was even necessarily clear that something could turn, that different feature of nature would turn into a computational advantage. But I think it would really blow his mind, and I think it would be very interested in the progress.
And Dave, dead or alive, but not both. Not both at the same time, right?
Well, very definitely alive. I'll choose someone who is here, John Preskill, one of the most respected people in our field of quantum computation. I've had a few brief interactions with him, but I would love to have a full dinner. So if John, if you're out there and available for dinner, I'm available.
And Theo?
I guess given the name of our qubit, I should go with Schrödinger, but not sure I want to have dinner with the guy. I mean, you'll do your research. So I'll go with another founding father of quantum mechanics. I guess Dirac. was really a brilliant personage. But the reason why I'd love to have dinner is because what we're currently doing is not just building a machine for technological purposes. I love this quote from a philosopher of science of the early of the previous century. We understand nature by resisting it. And building a logical qubit is really trying to escape decoherence. And the first proper logical qubit, which I'd argue didn't happen yet, would be really sort of a Sputnik moment. Just like Sputnik escaped gravity for just 3 months and was completely useless, beeping out there, the first logical qubit has the same symbolic meaning of escaping decoherence. And that would be a great platform to better understand what is decoherence, what is the frontier between the classical and the quantum world.
And just an anecdote, on Tuesday I got lucky and was at a dinner table with Professor Preskill. And he said, oh, I had plenty of dinners with Feynman. So, so why don't we go to the audience a little bit? These photons are really terrible. So who wants to go first? Who's got the first question?
Hey, thanks everyone. So my question is, with some of the kind of confidence and prospects for exciting non-scientific applications in the NISQ era, potentially on the wane, and the emphasis on error correction and fault tolerance, which is so incredible to see all the progress, how do you all think across your organizations about engaging with the kind of like long-term end users, the enterprises, the customers are going to be using this stuff, while staying consistent with your focus right now on building logical qubits?
Maybe I'll do a short answer. The way we interact with clients is by being very blunt about the resource estimation. I think the field is really at a tipping point where we're about to get to logical qubits, so there is no reason to be shy or to try to fuel the hype. And when you want to tackle one use case, you can actually put numbers and see in everyone's roadmap where does this fall, how many qubits, what kind of fidelity would you need to be relevant compared to classical machines. And it's not that daunting. I mean, when you're a big corporate and you're told, well, your use case might be feasible between 6 to 8 years from now, well, it's already time to get moving if you want to be the first there and have this first mover advantage. So we're pretty blunt about the resource estimation.
Anyone else want to chime in?
I can comment, even though if you have questions, our head of applications, Sam, is in the audience. So we actually engage with them on looking at their use cases, how do they map to algorithms that are known, and then we do resource state estimates of those use cases to essentially look at what kind of generation machine in terms of like ones that we have in our roadmap, but as well as like what kind of computational power would they need in order to solve those sort of problems. And actually, if you want examples of our work in that area, our applications teams do publish some of those resource estimates with that in collaboration with some of our external collaborators and customers.
We had an interesting experience at Quera when we previewed the release of announcing the Harvard-led work for the 48 logical qubits with some customers. And they said, oh, we've got these 2 algorithms that we want to try with 48 logical qubits. So I'm really curious. I don't know what they are, but I'm really curious to find out what is it that they think they could actually do with these qubits. But we'll find out. Who's got the next question?
If we haven't had the Sputnik moment yet for logical qubit, what is your criteria for what that Sputnik moment will comprise of?
I could recognize that voice in the dark.
So I guess in my personal opinion, the closest we are to that is Google experiment, where you have repeated cycle of error syndrome measurement, and you do what you would do with a quantum memory there. And what Google experiment showed is that they are just at threshold. So the Sputnik moment for me is to be significantly below threshold, show the exponential scaling as you increase the distance of the code, and you also manage to be break even. So those are the keywords you should be looking for. Repeated cycle, break even, below threshold.
So I'll disagree a little bit. So spice it up here a bit. So I would really want to see entanglement involved, right? I think it's very important that quantum memory is one thing. I think without doing logical entanglement and then with a QEC cycle or several QEC cycles showing improvement, I wouldn't put it at that Sputnik moment. I'm also one that kind of feels there won't be a singular moment. I think there's going to be, there's lots of moments that have already happened that I'm quite excited about, and from our team, from the teams represented up here, that I think, we all should feel very proud to be part of that work. I think there'll be more than one moment, right? I think it'll be a series of things, but I would add that, I really think you need kind of entanglement at the logical level and then QEC cycles and showing improvement to really start saying you're there.
Yeah, I think both answers have been great, and I would love to see all of that. I think there's one more requirement I would like to add, which is it has to demonstrate to us that it will scale. That is not, we don't stop at one logical qubit, because scaling is hard, and we need to make sure that it's not just something that works in a lab setup, in a very contrived experiment. It has to be scalable. We have to be able to control it scalably. We have to have solved the problems of, for example, cooling, like all of the platforms require cooling of some sort through cryogen, through other techniques. But you want to make sure that there's something that it will scale to what is required, because otherwise it just remains, well, a really interesting experimental demonstration of a feature of quantum mechanics, but not really something that we can see how it scales and we can operate applications on.
I cannot disagree, because the next 3 milestones on Google's roadmap are the logical memory, or the quantum memory, long-lived logical qubit, the entangling of logical qubits, and then the next milestone is called scaling.
Wonderful. As if we planned it in advance.
We
right?
didn't rehearse.
Theo, you mentioned, and I want to go back to the audience in a second, but you mentioned codes, code size. And do you think that over time there's just going to be one code that everyone uses in terms of encoding or code size, or we'll still be in a world where there are 17 different codes for 17 different applications?
I mean, when you think about it, the other place where you have the most impact with error correcting codes are telecommunications. And what differentiates, in my opinion, most generation of communication is generation of codes from more advanced. And I think current 5G runs on LDPC, if I'm not mistaken. This is why there is so much effort currently in the community. Now, each codes come with different constraints in terms of hardware requirements, in terms of overhead to decode them, how complex it is. And for example, there was a beautiful paper on quantum LDPC by IBM this summer, where they show a nice trade-off where they don't need all-to-all connectivity, but still something like 7th nearest neighbor, which is somewhat challenging, and they don't know yet how to do gates as far as I know. So see, you have trade-offs, and each platform will be more or less suited to answer those.
Anyone else want? I mean,
I would like to say something, which is I completely agree that codes will keep evolving. One thing is that codes can be, like, some codes are much more tailored specific to the specific hardware, and currently we have sitting here atoms, neutral atoms, ions, superconducting qubits, cat qubits, photonic qubits. Our quantum computer is going to be made of all of them? Well, we don't know, right? Like, we all think that the technologies are good, and what for photonics might be something that is much easier, maybe it is harder for other technologies, and vice versa. And some of these codes have features that are more amenable to specific technology platforms. So I think it's very difficult to answer the question, will we have one code or many codes? Because, well, number one, in the previous panel, there was discussion of concatenated codes, which I think is something that, it's only reasonable that is done at different scales. But second, it is like the code will have to adapt to the platform in which it is implemented on, and vice versa. Actually, like, co-design of these two things is something very important. So I think I'm sure we will see evolution of codes for different platforms. But the physical features of that platform will play a really big role in what are the error correcting codes that are applicable.
Concatenated codes. That sounds like something for you. If they
Cat
go to the
cat qubits are concatenate code, and one could argue that that way it's a Bacon shortcode in some sense.
I want to take another audience question and then go back for a lightning round, but I'm going to telegraph my question so you have time to think about it. And the question is when? When are we going to have quantum error correction in sort of a usable state? But before that, who's got the next question?
Is there a place in the world for a multimodal quantum computer?
You mean cross technologies, hybridizing? I think so. So, for example, you have some very nice proposal hybridizing spin qubits to superconducting qubits, because you could spin qubits can have very high density. So yeah, I mean and photonics are very well suited for telecommunications. It's harder to, I mean, if you want to interface a superconducting qubit based machine to the outside world, let's say in a far future when you want to connect either to quantum sensors for quantum machine learning application on quantum data, not classical data, or to build this quantum internet thing, then we'll have to interface with photonics. So naturally, in my opinion, yes, there is. But yeah, just like you have static RAM, dynamic RAM using different technologies, you have plenty of components using different technologies in classical compute.
I would just say that one of the things that has always fascinated me personally about photonics is that, I cannot say that there will only be photons in a quantum computer, but I can tell you there will be photons in a quantum computer. Maybe not alone, but there will be photons.
So let's get to the when question. Dave, you've been quiet.
Yeah, so the only future date that I'm going to talk about is the date of the immediate next milestone. And we think it's going to take us at least until 2025 to make the long-lived logical qubit.
Russell?
Yeah, I mean, to me, this one's even more difficult to define than the Sputnik moment, right? I think that can mean a lot of different things. I guess, maybe your threshold is when we're actually running on the logical layer an application or at least circuits that could not be classically simulated would maybe be one. I think we've been very careful in making big promises with dates, and then where we could potentially kind of deflate the industry by not making it. So I'll probably not put out a specific date for that particular milestone. I think, but it certainly is a matter of when, not if, at this point. And I think when I was starting 7 years ago on the Honeywell sort of commercial quantum computing effort, it was more if, and now I think it is when. But I think I think we're approaching it from a lot of different angles, and it's a very interesting race. But I will decline to put exact dates on where we're going to be.
So I will not say a specific date, but what I will refer everybody back to is the talk that our one of our co-founders gave, Pete Shadwell, where he announced some engagement that we have with SLACs to be able to have enough cryogenic power for our systems, and the work that he showed that we have already demonstrated in our lab in Daresbury, UK, where we are doing photonic interconnects, or we're building photonic interconnects between different cryogenic chambers that will contain a lot of our hardware. So this gives you an idea of the scale of the systems that we're working towards, and maybe given that things are being manufactured as of now, it gives you an idea that we're very serious about doing this in a very short time scale.
So I think what we said tonight is really that it's not a singular moment. passing to this era. But what we've seen over the last 2 weeks is so exciting. I mean, announcement across platforms with brilliant results everywhere, in, especially QA yesterday, but not only. I think we're definitely in this interface moment, going from NISC to FTQC. It's hard now to argue that FTQC won't happen. So the question is, when are you interested? Well, I'd argue it would be really nice to have somewhere between 50 to 100 logical qubit with 10 to the minus 6 or better error rates. And hopefully this should happen before the end of the decade for sure.
So if you asked me that question yesterday, I don't know what I would have said. But this morning, Vladan Vuletic, one of our scientific co-founders, had this last slide, and it says, in 2 years, we're going to have 100 qubits at 10 to the minus 6 to 10 to the minus 8. I immediately took a picture and slacked it to our engineers, said, I'm coming to pick it up. I don't know if he meant in the lab or on the cloud. I'd like to hope that it's in the lab. But Mercedes, Dave, Russell, Theo, thank you so much for spending time with me and with us today.